Good morning, everyone. Yesterday we have started chapter 3, Boolean logic, in which we discussed about three basic operators, which are AND, OR, and NOT. Today we will discuss about tautology, fallacy, and logic gates. So before these topics, let's discuss the truth tables again. Tables, what we are doing in truth tables, we are writing the inputs and the possible output. See, suppose this is the truth table for NOT operator. So in NOT operator, what we are doing, NOT operation are actually the unary operation. Unary operation means where only a single input or single variable is there. Fine. So in NOT operator, only one variable is there, one input is there. So one input can be either 0 or 1. So what we are doing, we just complement the value or just reverse the value. If the input is 0, then the output will be 1. Input is 1, the output will be 0. So actually what we are writing in input side, this row, this column, what we are writing, the possible input values. So for single operator, how many possible input values will be there? Either it will be 0 or it will be 1. Now when we have a truth table with two inputs, what actually we are doing? We are having how many possible combination we have to write here in input part. See, like in maths, you have must have done questions like when we are tossing two coins, what are the possible combinations? In probability, you must have done. What are the possible combination when we are tossing two coins? Combinations will be either the first coin is head, other is also head, either first coin is head, other is tail, either the first coin is tail, other is head, and both are tail. These are the four possible combinations. Similarly, here also, if we have two inputs, what are the possible combinations? The value of x can be either 0 or 1. Similarly, y can be either 0 and 1. So only two values are there. So possible combinations for these two inputs will be these values which we have written. So for two inputs, we have four possible combination. So this is the first combination, second combination, third combination, and fourth combination. And for these combinations, we have their output. So if the x first input is 0, other y input is 0, the output will be also 0. If first input is 0, other input is 1, the output is 1. So for these possible combinations, these are the required outputs. Now if we have three input, then what we'll do? See, this diagram will clear you a lot of things. When we have two inputs, what we are doing? The formula for getting the possible combinations are for two inputs, the formula is 2 to the power 2. How we got the formula? See, how many possible outcomes can be there? The output will be either 0 or 1. So two outcomes are there. So in base we have written 2. And this power 2, because we have two inputs, so we have written power 2. 2 to the power 2, that means 4 combinations. So for two inputs, we have 4 combinations. When we have three inputs, how many combinations we are there? Are there 2 to the power 3. How it come? Two possible outcomes. That's why the base 2 and 3 inputs are there. So 2 to the power 3. 8 combinations are there. Similarly, if we have 4 inputs, then 2 to the power 4 combination. If we have 5 inputs, 2 to the power 5 combination. See, if we'll notice these values, these are nothing but the binary equivalent of the decimal value. This is the binary equivalent of 1, 2, 3, and 4. This is value 1, 2, 3, 4. This is combination 1, 2, 3, 4, 5, 6, and so on. And for these, this is binary equivalent of 1, 2, 3 up to 15. See, 16 combinations are there. So these are the possible values of 0 to 15. These are 8 combinations. So from 0 to 7. These are 4 combinations from 0 to 3. This we have discussed when we were discussing the conversion. See, these are the binary values of decimal equivalent from 0 to 15. You don't have to learn these values. There's a easy method. What is the easy method? I have told you earlier also. We can start from 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So for 2 to the power 0, the output is 1. That means 1 bit difference you will write. You will start from 0, then 1, 0, 1. Then 2 to the power 1, 2, output is 2. Then we will give 2 bit difference. 0 0 1 1 0 0 1 1 and so on. Then 2 to the power 2, that is 4, so we'll give a difference of 4 4 4 times 0, 4 times 1. Then 2 to the power 3, then 8 times 8 times 0, 8 times 1. This is a shortcut method of remembering the decimal binary equivalent of these decimal values. So when we are writing these truth tables, so these are actually the binary equivalent of 0 to 15. These are binary equivalent of 0 to 8. These are binary equivalent of 0 to 3. This is 0 to 7, sorry. Fine. So in this way we can write the truth table. So what we are doing in truth table, if we have 2 inputs, then 4 combinations are there. If we have 3 inputs, 8 combinations we are making. If we have 4 inputs, 16 combinations we are making. Fine. Now let's move on. Now we'll discuss tautology. Tautology is nothing but when a binary expression, when in a binary expression the output is always true or 1, then it is called as tautology. Suppose we have this expression and we have to show that it is tautology. So what we'll do, first we'll write all the possible combination of these two inputs. See, we have two inputs here, x and y. We'll make the truth table for two inputs. Two input means 4 combinations. So we'll write the possible combinations and then we'll make the truth table for this expression. So this is the required output here. Now see, in this output all the outputs are true, or we can say 1. So that's why this truth table or this expression is showing tautology. Now next is fallacy. Fallacy is reverse of tautology. When the output shows all false values or 0, that means it is showing fallacy. Suppose in this expression you have to show that this expression is fallacy. So what we will do, we'll make the truth table for it. How many inputs are there? Only x and y. So 2 inputs are there. 2 input means 4 possible combinations. So we have write all 4 possible combinations and just make the truth table for this expression. Fine. This is the possible outcome. So all the output values, see, for all the possible combination, this is the output value and all are 0, or we can say false. That's why it is showing fallacy. Now one of the most important topic of this chapter is logic gates. Now what actually are logic gates? See, all the machinery, all the electronic device are having a circuit, and gates are nothing but the building block of these electronic circuits. Fine. So in your mobile phone, SoC is there. Fine. It is consisting of multiple chips combined together. So these chips are having circuits, and the building block of those circuits is only called the gates. So gates are nothing but the building block of any electronic circuit that has 2 or more inputs and 1 output. See, you are giving either it will be 1 input, 2 input, 3 input and more inputs. And a logical operation will held here through gate, and there will be only 1 output for these all inputs. Fine. So basically we can say that gates are digital circuits. Why we are calling them digital? Because the input value can be either 0 or 1. So digitally we are dealing, only 2 digits are there, 0 and 1. So we can say they are digital circuits because the input and output signals are either low, that is denoted by 0, or either high voltage. See, the input and output, these inputs and output will be either 0 or 1, or we can say 0 is represented by low voltage or 1 is represented by high voltage. We are discussing circuits. Now we'll come to language of voltage. So high voltage means 1 and low voltage means 0. So we have 3 basic logic gates, which are first inverter or NOT gate, second OR gate, and third is AND gate. Now first we are discussing NOT gate. See, NOT operator we have discussed yesterday. The same is with the NOT gate also. In NOT gate what we are doing, a unary operation will be held That means only one single input will be there. And for that one single input, one output will be there. Whatever the input is, suppose input A we are sending through this gate. Acha, this is the symbol for NOT gate, this triangle with a 0. So whatever the input we are sending, that is complemented. That means if we are sending 0, that will be 1 here. If we are sending 1, that will be converted as 1. So whatever input will give, the output will be reverse of that input. So for NOT gate, what we are doing, only one input will be there, that will be unary operation. One input will be there and one output will be there. The output is sometimes called complement, or we can say opposite of the input. So we can say this output is complement of the input or opposite of the input. This is the truth table which we had discussed yesterday only. Now next is OR gate. In OR gate, there can be two or more than two inputs, but only one output signal will be there. See, this is the symbol of OR gate. And suppose we are sending two inputs, A and B. So for these two inputs, only one output will be there, the output O. Now this A can be either 0, either 1. The B can be either 0 and either 1. Possible combinations, 4 possible combinations will be there. But the output will be only one value. Similarly, if we have 3 inputs, fine. Then for 3 inputs, there also will be only one single output. See, what we are doing in OR, what we are doing with OR operator, what we are doing, we were just adding, logically adding the inputs. So here the output will be O is equal to A plus B. If we have 3 inputs W, X, Y, then in that case the output will be W plus X plus Y. Now next gate is AND gate. In this also we have two or more than two inputs but only one output. When all the inputs are high, that means if both are high or 1, the possible outcome will be always 1. See, in logical multiplication, what was happening? If all the values were 1, the output is always 1. But if a single value is 0, if a single input is 0, the output will be always 0. See, the AND gate is represented by this D symbol. We have two inputs and one output. Fine. So O can be represented as A dot B. Dot is a symbol of AND operator. So what we are doing? We are doing logical multiplication. So if any of these two outputs is 0, the output will be always, if any of the two input is 0, output will be always 0. Similarly, we have three inputs here. If any of these three input is 0, the output will also be 0. And suppose we have three inputs W, X, Y. The output is Z, which is equals to W, X, Y. Logical multiplication of these three inputs. So if any of the input is 0, the Z will also be 0. If all three are 1, then Z will be also 1. Now that's it for today. Thank you.